Hello everyone, so this is a video lesson on force systems. Force can be defined in several ways, and most simply it can be defined as the cause of change in the state of motion of a particle or a body. And of course it can be defined as the product of the mass times the acceleration of the body. It is also a vector quantity, thus the direction is very important. Force can be also used to describe the mechanical interaction between bodies. So for example, in this picture, when the player kicks the ball, a certain force is applied from the foot of the player to the ball. Okay, and in return the ball exerts an equal but opposite force on the foot of the player. Force is also described as the manifestation of action of one particle on the other. So it can affect both the motion and the deformation of body on which it acts. So for example, in this picture, after a car crash, the force caused by the collision caused the car to change in motion from a certain velocity to zero velocity, and it also caused damage to the car. Forces can be classified as contact and non-contact. Contact forces are interactions between objects that touch. So for example, applied force or a force done by a spring, drag force, frictional force, and normal force. For non-contact forces, these are attract or repel even from a distance. So the direct interaction or direct contact is not required for these forces. For example, magnet force or magnetic force, electric force, and gravitational force. Forces have four major characteristics. The first one is the magnitude, which can be represented graphically by drawing a vector to scale. So for example, this is a vector F force which has a magnitude of 4 kilonewtons. The length of the vector represents its magnitude, so the longer the length of the vector, of course, the higher the force. And next is the direction or sense. So the sense or direction of a force is specified the direction. It can be positive or negative, in which the force moves along the line of action. So graphically, the sense can be represented by the arrowhead here pointing in the active direction. So since this vector is pointing towards the point B, so that means the force is acted or applied to point B. And next is the point of application, which is the exact location in which a force is applied to a body. So this point is usually described by a set of coordinates and is represented graphically by the tip of the arrowhead. Again, so this is where the force is applied, so on the tip of the arrowhead. So the point of application is unique to each force. And lastly, the line of action, which is called the line of, also called as the line of application. So it is geometric representation of how the force is applied. So in this case, the line of action is from A, so the line segment connecting A and B, through which the force is applied in the same direction as the vector F. When a mechanics problem or system has one or more forces acting on it, it is known as a force system or system of forces. Now, when the lines of actions of the set of forces lie in a single plane, so which this is called coplanar force system, while when the line of action of all forces do not lie on one plane or a single plane, it is called non-coplanar forces system or non-coplanar force system. We have different types of force systems for coplanar and non-coplanar. So for coplanar, we have collinear, parallel, concurrent and non-concurrent force systems. For non-coplanar, we have two. We have parallel, concurrent, and non-concurrent systems. We can say that it is a collinear force system if the lines of action of all forces of the system act on the same line. So as shown here, this force is called collinear force system. Now, if forces whose lines of actions are parallel with each other, it is called the force or parallel force system. So as shown here, F1, F2, and F3 are parallel with each other even though they are applied at different points. For a concurrent force system, the lines of actions of the sets of forces intersect at a common point. So for example, in this picture, forces F1, F2, and F3 intersect at point O. Therefore, it is a concurrent force system. Now, the forces, when extended, pass through this single point, and the point is called the point of concurrency. The lines of the action of all forces meet at the point of concurrency. Now, concurrent forces may or may not be coplanar. Now, lastly, we have non-concurrent force systems in which force whose lines of action are not concurrent and not parallel. As you can see here, this force, which is 2,400 pounds, and force P and Q do not meet in a certain point, and also they are not parallel with each other. So therefore, this system or force system is considered as non-concurrent. In most force system problems, we are asked to calculate the resultant of the force system. So the resultant of the force system is the simplest system that can replace the original body system without changing its external effect on a rigid body. Now let's recall some of the ways in calculating resultant force which were discussed in our previous lessons. So the first one is the vector addition, which is, for example, if we have vector A and vector B, so we can just simply get the vector sum of vector A and B to get the resultant. We can also use triangle method and parallelogram method in getting the resultant force. We also studied how we calculate the resultant force using the laws of sines and laws of cosines. Now, for example, a system of three vectors, F1, F2, and F3, and all of these vectors have their own three-dimensional components. We can say that R, or the resultant vector R, is equal to the summation of the three forces, which is equal to F1 plus F2 plus F3. Notice that I use symbols that has arrows at the top to indicate that this resultant force is calculated by getting the vector sum of these three forces. Now, in order to get the components of the resultant vector R, so let's say Rx, we can get the magnitude or the summation of the magnitude of Fx, while Ry, it's the summation of Fy, and for Rz, it's the summation of the components Fz. Now, another example, if you want to get the resultant vector of force F1 and F2 in which the angle between them is not equal to 90 degrees, which means this will not produce a right triangle, we can get the magnitude of the resultant vector using cosine law, which is r squared is equal to F1 square plus F2 square minus 2 F1 F2 cosine gamma. So notice that gamma here is opposite the resultant vector r. okay, is the opposite angle of the vector r, or resultant vector r. Now, if we will use this, okay, if we will use this angle phi, so we can use r square, or we can calculate for the resultant vector using this equation, f1 square plus f2 square plus 2 f1 f2 cosine phi. Okay, so this will be, notice that this is positive if the angle we use is not the angle that is opposite with the resultant vector r. There are problems where Polygon method is very useful in visualizing and calculating the resultant force of three forces. So for example, in this system with three forces, F1, F2, and F3, the best way to analyze this is to redraw them, or redraw the forces into a coordinate system. And then after that, we can do the Polygon method. So first is to draw F1. Okay, so here, so from here I took this F1 and then right here, and then next is to draw F2, or the second force, from the tip of F1. So there it goes, and then after that, we can now get the resultant vector of F2 and F1. So by drawing the resultant from the tail of F1 to the tip of F2, and after that we can draw F3 from the tip of F2, and then so since F3 is directed towards this, so just copy it here, and then by doing that we can get the resultant vector R123 by drawing the resultant vector from the tail of F1 to the tip of F2. Now here the sequence of drawing the different forces, it does not matter, so you can draw it the other way. So for example, here we can draw F3 first. So since F3 is directed this way, and so we can draw it this way, and then connect F1 or even F2. So you can draw any it in any sequence. So from the tip, as long as you draw it from the tip of or the head of the first arrow, and then yan. So F1 here and then F2. So from here, we can get the resultant vector of F3 and F1 here. Then finally, after drawing F2, we can get the resultant vector R3, 1, 2. So here. So basically, it is a repetition of finding the resultant of two forces. You just repeat the process. And the sequence of the addition process is arbitrary, meaning you can do any sequence. You can add, you can draw the different forces in any sequence. And the Polygon method becomes tedious when dealing with three and more forces, so it becomes harder, and it's getting worse when we deal with three-dimensional cases. That's why when we have three-dimensional cases, or when we have more than three forces in a system, we can use the rectangular component method. So the first example is we have three vectors. Vector A, or force A, is 100 newtons 37 degrees, while B is 100 newtons 150 degrees, and C is 80 newtons 233 degrees. So the best way to calculate for the resultant vector is to use the rectangular component method. So let's separate the components into R, X, and RY. So this is A. So the components of RA is 100. So for getting the Rx, or the component of X, or the component X, is R100 cosine 37, while for RY is 100 sine 37 degrees. For B, so same thing. So 100 cosine 150 degrees, and then for this is 100 sine 150 degrees. And for C, okay, so this is 80 cosine 233 degrees and 80 sine 233 degrees. Now we can calculate the sum of this. So for this it's 54.88 newtons, and this is 46.29 newtons. Note that this will be negative, or 54.88 newtons to the left. So if you will draw the resultant vector, it should be on the negative x direction and positive y direction. So it can be like this. And then we have to know theta. Okay. Now first let's get the value of the magnitude of the resultant vector, which is r is equal to square root of 54.88 square plus 46.29 square. That would be equal to 71.8 newtons. So this is the magnitude r. Now, so let's get the theta here. So we know that tan theta is equal to ry over rx. So this means it's ry is 46.29 newtons divided by 54.88 newtons, and theta is equal to arctangent this 46.29 divided by 54.88, which is equal to 40.15 degrees. So this is our theta. Now note that this theta is with respect to the negative x axis. So if you want to know the angle between this vector and the positive x-axis, let's say this is phi, we can just subtract phi is equal to 180 degrees minus r theta, which is 40.15 degrees, which is equal to 139.85 degrees. Therefore, our final answer is r is equal to 71.8 newtons, 139.85 degrees. So this will be our final or resultant force. So we have to put an arrow at the top since it's already a vector quantity. Now the next problem is for us to find the resultant force and the angle between r and the x-axis. So we are asked to get the resultant vector of these two forces, 900-pound force, which is 35 degrees from the x-axis, while this 600-pound force, which is 40 degrees from the first force. Now we can redraw this using this. We can just draw a parallel line here, parallel with the other force, and then of course we can also draw a parallel line here, and then the intersection, we can draw the resultant vector from the tail of the two vectors and then to the intersection of the parallel lines. We can also draw this using the head to tail method. So if we have this, so we can draw the first vector, 900 pound here. So this is 30 degrees. And then we can draw the second vector from the tip of the first vector, which is 600 pound. So this is 900 pound and then 600 pounds. Note that this is 40 degrees with the first angle. Now we can draw the resultant vector from the tail of the first to the tip of the second. Okay, here. So now this is our resultant vector r. And what we're looking for is the resultant, or the magnitude of this r and its angle theta with respect to the positive x-axis. For us to easily get that, so we can set this angle as alpha. So first, let's calculate the resultant vector, or the magnitude of the resultant vector r, which is r squared is equal to 900 square plus 600 square. So I'm using the cosine law, plus 2 times 900 times 600 times cosine. Note that I used positive here instead of negative, since we don't have any value for the angle opposite the resultant vector r. So I'm using the 40 degrees. That's why I used positive here. So 40 here. Or if you want to use the angle here that is opposite the r, you can just make it 900 square plus 600 square minus 2 900 times 600 and then cosine. So since this angle and the inner angle here that is opposite r forms 180 degrees, so 180 minus 40 is 140 degrees. So you can use any of the equations here, and this will give us the value of r as 1413.27 newtons. Oh, sorry, it's measured in pounds. Now, given this, we can get theta. But before that, let's first get the value of angle here, alpha. So since if we have a triangle, so if we have a triangle here, so this is alpha, and this is 140 degrees, and we know the value of this r, and we also know the value of the angle up, or the side opposite the angle alpha, which is 600 pounds. So we can get alpha using the sine law. So sine alpha divided by the angle, or the side opposite it, so which is 600, is equal to sine of, okay, so this 140 here divided by the magnitude of r, which is opposite the angle 140, so which is 1413.27. So that gives us a value of alpha, which is equal to 15.836 degrees. Now we already know the value of alpha. So in order to get the angle between the resultant vector and the positive x-axis, we can just simply add the 30 degrees and the angle alpha. So therefore theta is equal to 15.836 degrees plus 35 degrees is equal to 50.8 degrees. So therefore our resultant vector now is equal to 1413.27 pounds, 50.8 degrees. So this is our final answer. Now in this problem, we are asked to determine the components of the force, which is R is equal to 1,500 newtons. Now we will find the components Fu, which is parallel with the line U, and then Fv, which is parallel with line V, or directed towards V. Now the first thing we have to do is to redraw this. So first we have to draw Fv, so which is directed towards this direction. Note that this is 40 degrees, and then the next one is Fu. So this is Fv, and then this is Fu. We will draw it from the tip of Fv. So this is Fu, which is 30 degrees with the horizontal. Now the total R is directed here, so which is 1,500 newtons. So R is equal to 1,500 newtons. Note that this is also 30 degrees. So since they are alternate interior angles, which gives us the value of this angle as 110 degrees. Now, for us to find the components of R, which is Fu and Fv, so let's calculate Fu first. So Fu is equal to, so we will divide this Fu with the angle opposite, or the sine of the angle opposite it. So the angle opposite it is 40, so let's write sine of 40 degrees. It's equal to the R, the magnitude of R, which is 1,500 newtons, divided by the angle opposite it, which is 110. So that's sine 110 degrees. Now Fu will be equal to 1,500 times sine 40 divided by sine 110. So that is equal to 1026.1 newtons. And then now for Fv over sine of the angle opposite it. So the angle opposite Fv is 30 here. So we can write sine 30 degrees, which is equal to, again, let's use 1,500 newtons divided by sine 110 degrees. Now Fv is equal to 1,500 times sine 30 divided by sine of 110, which is equal to 798.1 newtons. Now we already have the components. Fu is equal to 1,026.1 newtons, while Fv is equal to 798.1 newtons. Now in this problem, we are asked to get the force F required to keep the particle O in equilibrium. So in order for this particle to be in equilibrium, first we have to get the resultant vector of these three vectors, F1, F2, and F3. And after that, the resultant vector should be the complete opposite of the force F, so that they can cancel, and then after that the particle O will be in equilibrium. Now, so we can use the rectangular component method to solve this problem. This time it's easier if we will use the IJK notation. So let's express these forces in IJK notation. So for F1, so it's on the positive y-axis, so that's 400 J hat newtons. So since it's positive, it's on the positive y-axis. And then F2 it's on the negative z-axis, so therefore it's negative 800 k hat newtons. While for F3, notice that F3 has three components, so which is the first component is on the positive y-axis, and then the second component is 2 meters from the negative x-axis, and the third component is on the negative 3 here, negative 3 on the y-axis. So to get the vector f or f3, so we multiply it with the magnitude of f3 times the r hat, or the components or the direction of f3 on the ijk notation or ijk direction. Now let's get the components of this r hat. So r hat is equal to r, the magnitude or the vector r, divided by its magnitude. So notice that this r hat represents the direction of f3. So r vector is equal to, okay, let's express this in terms of ijk notation. So since r, or the direction, or f3 is directed towards the negative x direction, and it's 2 meters to the negative x direction, so negative 2 I hat, and then again it's 3 meters away from to the negative y direction, so that's negative 3 j hat, and it's 6 meters on the positive z-axis, so that's positive 2, or so positive 6, sorry, positive 6 k hat, and then divided by the magnitude of this. So to get the magnitude of that vector, so that's 2 square plus 3 square plus 6 square. Okay, so now f3 is equal to the magnitude of f3, which is 700 newtons, times this r hat unit vector. So this is times negative 2i hat minus 3j hat plus 6k hat, divided by square root of 2 square plus 3 square plus 6 square. Now it's better if you will input this in your directly to your calculator, so that you avoid rounding off the answer. So let's do it one by one. So first, let's multiply 700, and then let's multiply it with negative 2i hat, and then this component. Okay, and that gives us negative 200 I hat. So when you input that to your calculator, so that's 700 times negative 2 over square root of 2 square plus 3 square plus 6 square, and then do it one by one per component. Now next one is 700 and 3j, so here, so that is 700 times 3 over this whole thing. Okay, 2 square plus 3 square plus 6 square. So let me use a darker color. Okay, so this is minus 300j hat. And then lastly, so the third component, 700 times 6k hat divided by this whole thing. So that's 700 times 6 divided by, so this is negative, so that's why it becomes negative. Okay, 600 square root of, sorry, this is 6, sorry, 6 divided by 2 square plus 3 square plus 6 square. Okay, that's why we have here plus 600k hat. So this is all newtons. So there. So to calculate the resultant vector r, so that is equal to f1 plus f2 plus f3, and we can calculate, to calculate that we have to add the common components. Like for example, j hat, we will combine it with j hat, and k hat, we will combine it with k hat. So notice that only f3 has negative or I component, so let's just combine it. That's 400 j hat, and then for f2 that is negative 800 k hat, and then plus this f3, so minus 200 I hat, and then minus 300 j hat plus 600 k hat newtons. So to combine j hat with j hat, and then k hat with k hat, and then I hat with I hat, so that is equal to negative 200 I hat plus 100 j hat, and then minus 200 k hat, and then all of this is equal to newtons, or I mean the unit is newtons. Now, so this will be our resultant vector r. This is r. However, we are looking for r, or for f, which is the complete opposite of the vector r. So therefore, f is equal to, so this is vector r, just the complete opposite of this, so it's positive 200 I hat, and then plus, or since it's plus, it becomes negative here, negative 100 j hat, and then since negative, it becomes positive 200 k hat, and then this is newtons. So this is the final answer.